Hello everyone. Today we'll study expectation of functions of several random variables. Let S1, S2, Sn be random variables. With multivariable probability function or probability density function. F of S1, S2 up to Sn. Expectation of G of S1, S2, Sn is defined as the sum of all S1 in a support the sum of all S2 in the support of S2 and the sum of all Sn in the support of Sn. Take this function, the function in the parentheses, in the bracket, G of S1, S2, Sn times the multivariable probability function f of S1, S2, Sn. So if x is discrete random variables, we take the sum of all S1 in the support, S2 in the support, Sn in the support, then take function g in the parentheses times the probability function f of S1, S2 up to Sn. If S1, S2, Sn are discrete random variables, now if S1, S2, Sn they are continuous random variables, we take integral. So E of expectation of function g of S1, S2, Sn, those are capital letters. Those are capital X. They represent random variables. G is a function of random variables. For continuous random variable, we take integral from net infinity to infinity for all random variables, S1, S2, Sn, take integral from net infinity to infinities. Use function g in the bracket, g of S1, S2, Sn times f of S1, S2, Sn. Then it must be ds1, ds2 up to dsn. If S1, S2, Sn they are continuous random variable, now let's look at an example. Let x and y be discrete random variables with the joint probability function given in the following table. That's the joint probability function of x and y. Find the mean and the variance of x squared plus 2y. So let's find the mean first. The mean is the special value. Find the mean of x squared plus 2y. The mean is the special value. Since x and y they are discrete random variables, Since x and y, they are discrete random variables, we take the sum for all x in the support of x, and taking the sum for all y in the support of y. Then taking the function in the parentheses, x squared plus 2y. Here we use lowercase letters. For the function in the parentheses, this is a function of random variables. It must be capital letters. And for the function here, we use lowercase letters. Function g, that's function g, times the probability function f of sy. Then find the sum for all x in the support and for all y in the support. Here, for all s y in the support, we have s equal to 1, y equal to 2, s equal to 1, y equal to 4, s equal to 1, y equal to 6, s equal to 2, y equal to 2, s equal to 2, y equal to 4, and s equal to 2, y equal to 6. So find the sum, adding up. That means adding up. In the first box here, s is 1, y is 2. I have 1 squared plus 2 times 2 times f of 1 comma 2. In the first box here, s is 1, y is 2. 1 squared plus 2 times 2 times f of 1, 2. In the second box, we have 1 squared plus 2 times 4 times f of 1 comma 4. Next box, I have 1 squared plus 2 times 6 times f of 1 comma 6. Next row. Here, s is 2. In this box, s is 2, y is 2. I have 2 squared plus 2 times 2 times f of 2 comma 2. Next box, s is 2, y is 4. 2 squared times 2 times 4, f of 2 comma 4. Plus, here, x is 2, y is 6. I get 2 squared plus 2 times 6 times f of 2 comma 6. Then adding up. 1 squared plus 2 times 2 is 5 times f of 1, 2. F of 1, 2 is 0.10. Next, 1 squared plus 2 times 4. 2 times 4 is 8. 8 plus 1 is 9. Times f of 1, 4. F of 1, 4 is 0.20. Next, 2 times 6 is 12. 12 plus 1 is 13. I get 13 times f of 1 comma 6 is 0.30. Plus, next, 2 squared is 4. 2 times 2 is 4. 4 plus 4 is 8. 8 times f of 2, 2. F of 2, 2 is 0.10. Next, 2 squared is 4. 2 times 4 is 8. 4 plus 8 is 12. I get 12 times f of 2 comma 4. F of 2 comma 4 is 0.10. Next, plus 2 squared plus 2 times 6 times f of 2 comma 6. 2 times 6 is 12. 2 squared is 4. 4 plus 12 is 16. Times f of 2 comma 6. F of 2 comma 6 is 0.20. Then multiply and adding up. I get 0.50 plus 1.80 plus 3.90 plus 0.80 plus 1.20 plus 3.20. Then I use my calculator. I get 11.4. That's the mean of x squared plus 2y. That's the mean of x squared plus 2y. Next, let's find the variance of x squared plus 2y. Variance of x squared plus 2y. That can be written as expected value of x squared plus 2y squared minus expected value of x squared plus 2y squared. Because expected variance of any random variable is expected value of x squared minus expected value of x squared. So we apply the formula here. Treat this as x. Expected value of x squared minus expected value of x squared. Here we know expected value of x squared plus 2y already. We can plug in this number and square. We get this number here. For the first number, we must compute expected value of x squared plus 2y squared. We must compute this. So let me compute here. Expected value of x squared plus 2y squared. Here, this is the function of the random variables of x and y. Since x and y, they are discrete random variables, we take the sum for all x in the support and take the sum for all y in the support of y. Take the function in the parentheses, x squared plus 2y squared times f of sy times the probability function. Then find the sum for all x and all y. Here x could be 1 and 2, y could be 2, 4, and 6. Find the sum for all these boxes here. In the first box, x is 1, y is 2. So I get 1 squared plus 2 times 2 squared times f of 1 comma 2. Second box, x is 1, y is 4. I have 1 squared plus 2 times 4 squared times f of 1 comma 4. Next box, x is 1, y is 6. I have 1 squared plus 2 times 6 squared times f of 1 comma 6. Next row. In the first box here, I have x is 2, y is 2. So I get 2 squared plus 2 times 2 squared f of 2 comma 2. Next box, x is 2, y is 4. I get 2 squared plus 2 times 4 squared f of 1 comma 4. Next box, x is 2, y is 6. I get 2 squared plus 2 times 6 squared times f of 2 comma 6. Then calculate everything and plug in numbers. 2 squared is 4. 4 plus 1 is 5. 5 squared is 25. Times f of 1 comma 2. F of 1 comma 2 is 0.10. Next, 2 times 4 is 8. 8 plus 1 is 9. 9 squared is 81. 81 times f of 1 comma 4. F of 1 comma 4 is 0.20. Next, 2 times 6 is 12. 12 plus 1 is 13. 13 squared is 169. Times f of 1 comma 6. F of 1 comma 6 is 0.30. Plus, next, 2 times 2 is 4. 2 squared is 4. 4 plus 4 is 8. 8 squared is 64. Times f of 2 comma 2. F of 2 comma 2 is 0.10. Next, 2 times 4 is 8. 2 squared is 4. 8 plus 4 plus 8 is 12. 12 squared is 144. Times f of 1 comma 4. This should be f of 2 comma 4. F of 2 comma 4 is 0.10. Plus 2 times 6 is 12. 2 squared is 4. 4 plus 12 is 16. 16 squared 16 squared is 256 times f of 2 comma 6. F of 2 comma 6 is 0.20. Then multiply. 25 times 0.10 is 2.50. 81 times 0.20 is 16.20. 169 times 3 is 50.70. 64 times 0.10 is 6.40. 144 times 0.10 is 14.40. 256 times 0.20, that's 51.20. Then I use my calculator. I get 141.4. Next, we can find the variance. Variance of s squared plus 2y is the expected value of s squared plus 2y squared minus expected value of s squared plus 2y squared. The first part is 141.4. For the second part, expected value of s squared plus 2y is 11.4. So minus 11.4 squared. 11.4 squared is 129.96. Then subtract, I get 11.44. That's the variance of s squared plus 2y. Next example, let x and y be continuous London variables with joint probability density function f of sy equal to 1/18 sy squared if s is between 0 and 2 and y is between 0 and 3, 0 otherwise. Find the mean and the variance of 4s plus 3y. Let's find the mean first. The mean of 4s plus 3y is the expected value of 4s plus 3y. Since x and y, they are continuous London variable, we take integrals from net infinity to infinity, net infinity to infinity. Take the function in the parentheses, 4x plus 3y. Here we use lowercase letters. For the function in the parentheses must be capital letters, because this is a function of random variables. And for the function here, it must be lowercase letter, g of sy times f of sy times the PDF f of sy. ds, dy, or dy, dx. Doesn't matter. Next, in order to take this integral, we must draw the support first. We must draw the support. Here, support is the interval like x between 0 and 2, y between 0 and 3. And for the support, we must include all the boundaries. Here it's a rectangular region, such that s is between 0 and 2 and y is between 0 and 3. That's the support of s and y. Now take integral. Take integral over the support. For the support, the lower bound is y equal to 0. Upper bound is y equal to 3. Over this region, x is from 0 to 2. (4x plus 3y) times f of sy. In the support, f of sy is 1/18 times xy squared. dy dx. We must match the integral here, dy dx. Then simplify the integrand first. Simplify the integrand. distribute 4x, distribute 3y. If I distribute 4x, I have 2 over 9 s squared y squared. If I distribute 3y, I get 1 over 6 sy cubed dy times dx. Next, I take antiderivative with respect to y. Take antiderivative with respect to y. That's 2 over 9 x squared times y cubed over 3. 1 over 6 x times y to the power 4 over 4. Evaluate y from 0 to 3. dx. Then plug in 3, plug in 0, take difference. If I plug in 3 for y, 3 cubed is 27. On the bottom, 9 times 3 is also 27. 27 cancel 27. I get 2s squared. If I plug in 3 here, 3 to the power 4 is 81. 81 divided by 3 is 27. 6 divided by 3 is 2. So I got 27 over 4 times x, over 8 times x. If I plug in 0 for y, I get 0. Then times dx. Then take antiderivative with respect to x. I get 2s cubed over 3 plus 27 over 8 times s squared over 2. Evaluate x from 0 to 2. If I plug in 2, 2 cubed is 8. 8 times 2 is 16. I get 16 over 3 here. If I plug in 2, 2 squared is 4. 8 times 2 is 16. If I divide top and bottom by 4, I get 27 over 4. If I plug in 0 for x, I get 0. Then adding up. Common denominator here is 12. 4 times 16 is 64. 3 times 27 is 81. 64 plus 81 is 145. So the answer is 145 over 12. That's the mean. That's the expected value of 4x plus 3y. Next, we try to find the variance of 4x plus 3y. We know that variance of 4x plus 3y. That's the variance, that's the expected value of 4x plus 3y square minus expected value of 4x plus 3y square. We know expected value of 4x plus 3y. We know expected value of 4x plus 3y, which is 145 over 12. Next, we need to find expected value of 4x plus 3y square. Expected value of 4x plus 3y square. Since x and y, they are continuous random variable. Take integral from net infinity to infinity. Net infinity to infinity. Take the function in the parentheses. 4x plus 3y square times f of sy dx dy. Then we take integral over the support. For the support here, lower bound is y equal to 0, upper bound is y equal to 3. So we can integrate from bottom to top. Lower curve is y equal to 0, upper curve is y equal to 3. And over this support, x varies from 0 to 2. (4x plus 3y squared times f of sy f of xy in the support is 1 over 18 xy squared times dy, then dx. Now here we solve the inner integral first. Let me first of all simplify the inner integral. If I expand the perfect square, I get 16x squared plus 24sy plus 9y squared times 1 over 18 xy squared dy dx. Then I distribute 1 over 18 xy squared. If I distribute 1 over 18 sy squared, I have a over 9 s cubed y squared plus 4 over 3 s squared y cubed plus 1 over 2 sy cubed sy to the power of 4 dy dx. Then take antiderivative with respect to y. Leave the outer integral the same. Take the antiderivative with respect to y. I have a over 9 s cubed times y cubed over 3 plus 4 over 3 s squared times y to the power 4 over 4 plus 1 over 2x y to the power 5 over 5. Evaluate y from 0 to 3 dx. Plug in 3 for y. If I plug in 3 for y, y cubed is 27. On the bottom, 9 times 3 is 27. So 27 get cancelled. We get as cubed. Second term, plug in 3 for y. Y to the power 4 is 81. 81 divided by 3 is 27. 4 and 4 get cancelled. I get 27 s squared. In the third term, if I plug in 3 here, 3 to the power of 5 is 243 over 10 times x. If I plug in 0 for y, I get 0 everywhere. Then times dx. Next, take antiderivative with respect to x. I get 2s squared, 2s to the power of 4. Plus 9s cubed plus 243 over 20 s squared times s squared. Evaluate from 0 to 2. If I plug in 2, 2 to the power of 4 is 16. 16 times 2 is 32. If I plug in 2 here, 2 to the power of 3 is 8. 8 times 9 is 27. Sorry, 8 times 9 is 72. If I plug in 2 here, 2 to the power of 4. 2 to the power of 2 is 4. And 4 and 20, if I reduce it, I have 5 on the bottom. I get 243 over 5. If I plug in 0 for x, I get 0. So for the final answer, 32 plus 72 is 104 plus 243 over 5. Then, adding up, 104 times 5 is 520 plus 243. 520 plus 243 is 763 over 5. Then, for variance of 4x plus 3y, we use expected value of 4x plus 3y squared, which is 763 over 5, minus expected value of 4x plus 3y squared. Expected value of 4x plus 3y is 145 over 12. So, for variance of 4x plus 3y, we use expected value of 4x plus 3y square minus expected value of 4x plus 3y square, which is 763 over 5 minus 145 over 12 square. Here I use my calculator. The answer is 4747 over 720. 4747 over 720. That's the variance of 4x plus 3y. Next, let me introduce a theorem. Let S1, S2, Sn be random variables. With finite expectations. Finite expectation means for each random variable, their expected values are finite. Then expected value of S1 plus S2 plus Sn equal to expected value of S1 plus expected value of S2 plus expected value of Sn. That means for the expected value of the sum of several random variables, I can separate the terms, write it as the sum of the expected value of each random variables. And furthermore, for the expected value of A1 S1 plus A2 S2 plus An Sn, I can write it as A1 times expected value of S1 plus A2 times expected value of S2 plus An times expected value of Sn, which means for the expected value of a linear combination of several random variables, I can separate the terms. I can first of all separate each terms, and then pull out the constant, pull out A1, A2, and An. Next theorem. If x and y are independent random variables, then expected value of x times y equal to expected value of x times expected value of y. If x and y are independent random variables, then expected value of x times y equal to expected value of x times expected value of y. Let's prove it. This theorem is simple. Let's prove it. So, in order to prove this theorem, let's consider two cases. X and y could be either discrete random variables, or they could be continuous random variables. We must consider two cases. Case 1. X and y are discrete random variables. with joint probability function. F of sy. Then its special value of sy, that's the sum of all x in the support of x, and the sum of all y in the support of y. X times y times the joint probability function f of sy. Since x and y are independent random variables, they are independent random variables, then f of sy equal to the marginal probability function of x times the marginal probability function of y. And also, since the marginal probability function of x is identical to the probability function of x, and the marginal probability function of y is identical to probability function of y, they're equal to f1 of x times f2 of y, where f of f1, f2, they are probability functions of x and y. Where f1 and f2, f1 of x, f2 of y. They are probability functions of x and y. So its special value of x times y equal to the sum of all x in the support of x times all y in the support of y. Of sy times probability function of x times probability function of y. That can be written as here for the sum of y. I treat s as constant. I can pull out function of x. For the sum of y, I treat s as constant. I can pull out a function of x. So write it as the sum x belongs to support of x. I pull out x. Pull out f1 of x. What's left is the sum of all y belong to support of y. What's left here is y times f2 of y. And we know that this is the special value of x. This is the special value of x. And this is the special value of y. So that's how we prove E of sy equal to E of x times E of y. When s and y, they are discrete random variables. Now case 2, x and y, they could also be continuous random variables. Continue. Case 2. X and y, they could be continuous random variables. I forget variables. X and Y are discrete random variables. Case 2, X and Y are continuous random variables with joint probability density function. F of xy. Now, here is special value of xy. Since x and y, they are continuous random variable, we take integral from net infinity to infinity. Net infinity to infinity. X times y times the PDF, the joint PDF f of sy. ds dy. Since x and y, they are independent random variables, since x and y are independent random variables, then the joint PDF f of sy equal to the marginal PDF of x times the marginal PDF of y. And since the marginal PDF of x is identical to the PDF of x, and the marginal PDF of y, the marginal PDF of y is identical to the PDF of y. So I can write f of sy equal to the marginal PDF of x times the marginal PDF of y times the PDF of x times the PDF of y. Here, f1 of x and f2 of y, they are probability density function of x and y. They are probability density functions of x and y. Respectively. In the other part, it's also respectively. f1 of x, f2 of y, they are probability function of x and y, respectively. So, f1 of x, f2 of y, they are probability density function of x and y respectively. So, expected value of x times y equal to the integral from net infinity to infinity, sy times f of x, f of sy. That's f1 of x times f2 of y, dx dy. For the inner integral, since we're taking dx, we treat y as constant. For the inner integral, I treat y as constant. Since I'm doing dx, I treat y as constant. So I can pull out y, pull out f2 of y. I pull out y, pull out f2 of y. Pull out y, pull out f2 of y. What's left is integral from net infinity to infinity, x times f1 of x, dx dy. Now, this inner integral, that's a constant. When I take inner integral, that's a constant. A definite integral is a constant. A definite integral is always a constant. So I can pull it outside. I can pull this outside the parentheses. If I pull it outside, I have integral from net infinity to infinity, x times f1 of x dx. If I pull this outside, what's left is integral from net infinity to infinity, y, f2 of y. Since I pull this outside, what's left is dy here. This f1 is the PDF of x. This f1 is the PDF of x. So integral from net infinity to infinity x times f1 of x dx. That's the expected value of x. And this f2 is the PDF of y. The integral from net infinity to infinity y f2 times dy. That's the expected value of y. So when s and y are continuous London variable, expected value of sy is expected value of x times expected value of y. Here I prove expected value of x times y equal to expected value of x times expected value of y in both cases. So if x and y they are independent London variables, expected value of x times y is expected value of x times expected value of y. Next, let me introduce a theorem about variance. Let S1, S2, Sn be independent London variables. With finite expectation and variance. That means for every London variables S1, S2, Sn, their expected values and variance are all finite. For every London variables, their expected value and variance are all finite. Then the variance of S1 plus S2 plus Sn equal to variance of S1 plus variance of S2 plus variance of Sn. That means for the variance of the sum of several London variables, I can separate each terms, write it as the sum of variance of S1, S2, Sn. And furthermore, for variance of A1, S1 plus A2, S2 plus An, Sn, that equal to A1 squared times variance of S1 plus A2 squared times variance of S2 plus An squared times variance of Sn That means for variance of a linear combination of several London variables, I first of all separate each terms. Then for variance, when I pull out constant, I must square the constant. For variance, when I pull out coefficient, I must square the coefficient. So when I pull out A1, I square A1. When I pull out A2, I square A2. When I pull out An, I square An. Next, let me introduce sum of independent normal random variables. First of all, let's look at a theorem. Let S1, S2, Sn be independent normal random variables. Let S1, S2, Sn be independent normal random variables. That means S1, S2, Sn, they are independent random variables. And S1, S2, Sn, they all have normal distribution. And let the random variable y equal to A1S1 plus A2S2 plus ANSN. So let y be a linear combination of S1, S2, Sn. Then y also has a normal distribution. So this theorem says, if a random variable is a linear combination of several normal random variables, then this random variable also has a normal distribution. Next, let's look at an example. In a restaurant, assume it has a fixed daily cost of $2,500. The revenue from breakfast has a normal distribution with a mean and a standard deviation of $600 and $100, respectively. The revenue from lunch has a normal distribution with a mean and a standard deviation of $1,000 and $150, respectively. And the revenue from dinner has a normal distribution with a mean and a standard deviation of $2,000 and $400, respectively. Assume the revenue from the breakfast, lunch, and dinner are independent. Part A, find the mean and the standard deviation of the daily profit. Part B, in a given day, what's the probability that the daily profit is more than $1,000? Part C, in a given day, what's the probability that the daily profit is between $800 and $1,300? Let's do part A first. Find the mean and the standard deviation of the daily profit. So let's first of all write down the given information and set down the problem. For part A, we are looking for the mean and the standard deviation of the daily profit. Let A be C. Let random variables A, B, C represent the revenue from the breakfast, lunch, and dinner, respectively. Then A is the revenue from breakfast. A has a normal distribution. With mean of $600 and a standard deviation of $100. So the mean is 600. Variance is 100 square. B has a normal distribution. B represents the revenue from the lunch. So B has a mean of $1,000 and a standard deviation of $150. So the mean is 1,000, variance is $150 square. C represents revenue from dinner, so C also has a normal distribution. The mean is $2,000, and the standard deviation is $400. Mean is 2,000, variance is 400 square. That's what's given. Now let D represent a daily profit. Let D represent a daily profit. Let the random variable D represent a daily profit. Then we know that profit is revenue takeaway cost. We have revenue from breakfast, plus revenue from lunch, plus revenue from dinner. Take away the fixed daily cost. Here the fixed daily cost is $2,500. Revenue takeaway cost is the daily profit. And here we know that A, B, C, they are independent normal random variables. A, B, C, they are independent normal random variables. Since D is a linear combination of independent normal random variables, by the previous theorem, D also has a normal distribution. D has a normal distribution. Now we try to find the mean and the standard deviation of the daily profit, which is the mean and the standard deviation of D. Let's find the mean first. Mean is the expected value. Expected value of D is expected value of A plus B plus C minus $2,500. When we have expected value of the sum of several random variables, I can separate the random variables. Write it as expected value of A plus expected value of B plus expected value of C plus expected value of negative 2,500. Expected value of A is 600. Expected value of B is 1,000. Expected value of C is 2,000 minus 2,500. Then adding up, 600 plus 1,000 is 1,600, plus 2,000 is 3,600. Take away 2,500. That's 1,100. That's the mean of D. That's the mean of the daily profit. Next, we try to find the variance of the daily profit. We try to find the standard deviation of the daily profit. Let's find the variance first. Then take square root. We get the standard deviation. Next, let's find variance of D. Here, D is A plus B plus C minus 2,500. For variance of the sum of independent random variables, I can separate the variance. Write it as variance of A plus variance of B plus variance of C plus variance of negative 2,500. For the variance of the sum of several random variables, independent random variables, I can separate the variance if they are independent. Here we know that A, B, C, they are independent random variables. Since the revenue from breakfast, lunch, dinner are independent. For variance of the sum of independent random variables, I can always separate the random variables. Then variance of A is 100 squared. Variance of B is 150 squared. Variance of C is 400 squared. Variance of a constant is always 0. Variance of constant is always 0. Then here I use my calculator. I get 192,500. That's the variance. For the standard deviation, take square root of the variance. Square root of 192,500. Here I use my calculator. I get 478.75. So that's the standard deviation of the daily profit. That's why D. D represents daily profit here. And this is mu of D. That's the mean of the daily profit. That's the mean of the daily profit. That's the standard deviation of the daily profit. That's part A. Find the mean and the standard deviation of the daily profit. Part B. In a given day, what's the probability that the daily profit is more than $1,000? In a given day, what's the probability that the daily profit is more than $1,000? So in part B, we're looking for the probability that in a given day, the daily profit is more than $1,000. Since D has a normal distribution, we can change D to the standard normal distribution. Then use the table, use the standard CDF to find the probabilities. Since D has a normal distribution, I can convert D to the standard normal distribution. Then use the table of the standard normal CDF to find the probabilities. That's much easier than solving integrals. So let's convert. Formula for conversion is x equal to z equal to s minus mu over sigma. So if I convert D to Z, the formula is x minus mu, 1000 minus mu of D over sigma of D. Mu of D is 1100. Sigma of D is 438.75. Then use my calculator. 1000 minus 1100 over 438.75. If I use my calculator, round to 2 decimal places, I get negative 0.23. So we are looking for probability that Z is greater than negative 0.23. Since we try to use the standard normal CDF, I try to put it in the form of probability that Z less than some number, or probability that Z less or equal to some constant. Try to put it in this form. That equal to phi of Z. Both of them equal to phi of Z. Since the normal CDF is a continuous function, it doesn't matter if we include an endpoint, they both equal to phi of Z. So, since here we have Z greater than some number here, I can use the complement, write it as 1 minus probability that Z is less or equal to negative 0.23. That's the complement. Z less or equal to negative 0.23. That's phi of negative 0.23. That's phi of negative 0.23. Then use a table. Use a table of a standard normal CDF. Using a standard normal CDF. Negative 0.23. Negative 0.23. Here is 0.40905. 0.40905. So I get 1 minus 0.40905. Then subtract, I get 0.59095. In general, round answer to 4 decimal places. That's 0.5910. That's part B. The probability that daily profit is more than $1,000 in a given day. Part C. In a given day, what's the probability that the daily profit is between $800 and $1,300? For part C, we're looking for probability that D is between $800 and $1,300. Since D has a normal distribution, I can convert D to the standard normal distribution. Convert D to Z. If I convert D to Z, the formula is X minus mu over sigma. 800 minus mu of D over sigma of D. 1,300 minus mu of D over sigma of D. Then mu of D is 1,100. Sigma of D is 438.75. Plug in, I get 800 minus 1,100 over 438.75. Plug in here, I get 1,300 minus 1,100 over 438.75. Then I use my calculator. Round the answer to 2 decimal places. I get negative 0.68. And for the other one, round the answer to 2 decimal places. I get positive 0.46. Next, we try to use the standard normal CDF, the table of the standard normal CDF to find the probabilities. That means I need to rewrite probability in the form of probability that Z less than some number or Z less or equal to some number. This probability can be rewrite as probability that Z less or equal to 0.46 minus probability that Z is less than negative 0.68. If we need equal sign here, we don't include equal sign here. For the larger one, we keep the equal sign under inequality. For the smaller one, for the smaller number, if there is no equal sign, add equal sign. But if there is equal sign, remove equal sign under inequality. But since the standard normal CDF is a continuous function, it doesn't matter if we include equal sign. That's equal to phi of 0.46. That's function phi of negative 0.68. Then find a value from table and subtract. Find a value from standard normal CDF and then subtract. That's a table of the standard normal CDF. Phi of 0.46. Phi of 0.46 is 0.67724. 0.67724. minus phi of negative 0.CSTA. Negative 0.CSTA is here. 0.24A25. Then I use my calculator. When I subtract, I get 0.42A9. If I round the answer to 4 decimal places, I get 0.42A9. That's the probability that the daily profit is between $800 and $1,300. Next example. In a supermarket, there are apples and pears. Assume the weight of the apples has a normal distribution with the mean and the standard deviation of 180 gram and 50 gram respectively. And the weight of the pears has a normal distribution with the mean and a standard deviation of 200 gram and 25 grams. Part A. When an apple and a pear are randomly chosen, what's the probability that the apple weighs more than the pear? Part B. If the apples cost 3 cents per gram and pears cost 2 cents per gram, when an apple and a pear are randomly chosen, what's the probability that the apple costs more than the pear? Part C. When 3 apples and 2 pears are randomly chosen, what's the probability that the apples weighs more than the pears? Part D. When 3 apples and 2 pears are randomly chosen, what's the probability that the average weight of the pears of the apples is more than the average weight of the pears? Let's do part A first. When an apple and a pear are randomly chosen, what's the probability that the apple weighs more than the pear? Let's first of all write down the given information. Let A and B represent the weight of a pair of an apple and pear. In grams. Then both A and B has normal distributions. A has a normal distribution with mean of 180, standard deviation of 15. Mean is 180. Variance is 15 square. Variance is always standard deviation square. B also has a normal distribution. Mean is 200, and the variance is 25 square. Standard deviation is 25. Variance is 25 square. That's the setup. Part A. What's the probability that the apple weighs more than the pear? We're looking for the probability that the apple weighs more than the pear. We're looking for the probability that the apple weighs more than the pear. We can compare directly. So what we can do is I can move B over. We can compare A and B directly. So what we can do here, I can move B over. This probability can be rewritten as probability that A minus B is greater than 0. Now, next, let's create a new random variable. Let random variable x equal to A minus B. Let random variable x equal to A minus B. Then, by the previous theorem, x is a linear combination of independent X is a linear combination of independent normal random variables, then X also has a normal distribution. Since X is a linear combination of independent normal random variables, then X has a normal distribution. Since X is a linear combination of independent normal random variables, by the previous theorem, X has a normal distribution. Next, we try to find a mu, try to find a mean in the standard deviation of X. Let's find a mean first. Mean of X is the mean of A minus B. Let me rewrite this. Its batch derivative of A plus its batch derivative of negative B. That's its batch derivative of A minus its batch derivative of B. Its batch derivative of A is 180. Its batch derivative of B is 200. That's negative 20. So mu of X is negative 20. Mu of X is negative 20. That's mu of X. Mu of X is negative 20. Next, I'm trying to find the variance of X. Next, I'm trying to find the variance of X. Variance of X is variance of A minus B. Since A and B, they are independent random variables. Variance of linear combination of independent random variables. I can separate the random variables. Write it as variance of A. Be very careful. Variance of A plus variance of negative B. Be very careful. You must write it as variance of A plus variance of negative B. When we separate its special value and variance, it must be addition in the middle. Variance of A, I can consider this as A plus negative B. Consider this as A plus negative B. It must be variance of A plus variance of negative B. If you write it as variance of A, minus variance of B, you'll be wrong. That's wrong. We must write it as variance of A plus variance of negative B. We must consider this as A plus negative B. For its special value, it doesn't matter. If I pull out negative sign, that's exactly the same. For its special value, it doesn't matter. But for variance, we must consider this as A plus negative B. Write it as variance A plus variance of negative B. For variance, the sign matters. It must be variance of A plus variance of negative B. For its special value, it doesn't matter. If I pull out negative 1, it's the same as negative is special value of B. For its special value, it doesn't matter. But for variance, we must consider this as A plus negative B. Then we have variance of A plus, here consider that's negative 1 times B. If I pull out coefficient, I must square the coefficient. I get negative 1 squared times variance of B. Then variance of A is 15 squared. Negative 1 squared is 1. Variance of B is 25 squared. Next calculator, 15 squared plus 25 squared. Here I get 850. So for the standard deviation, I take square root for the variance. Which is square root of 850. We can leave it the way it is. That's the standard deviation of X. Now, We know A minus B is X. This probability can be rewritten as probability that X is greater than 0. Since X has a normal distribution, I can convert X to standard normal distribution. Then use the table of the standard normal CDF to find the probabilities. That's much easier than solving integrals. Let's convert. The formula is X minus mu over sigma. 0 minus mu. Mu is negative 20. Over sigma. Sigma is radical A50. X minus mu over sigma. After convert, this becomes Z. I convert X to the standard normal distribution. Next calculator. I get 20 over radical A50. Use calculator, round to 2 decimal places. I get 0.69. Use calculator, round to 2 decimal places. I get 0.69. Then, since we try to use the table of the standard normal CDF, I must put it in the form of Z less or equal to some number. Here I can use complement. I can use the complement here. That's 1 minus probability that Z is less or equal to 0.69. That's 1 minus phi of 0.69. That's 1 minus phi of 0.69. And then use the table, find phi of 0.69. 0.69 is here. That's 0.75490. 0.75490. 0.75490. If I subtract, answer is 0.2451. That's the probability that an apple weighs more than a pear. That's the probability that an apple weighs more than a pear. That's part A. Part B. If an apple costs 3 cents per gram, and pears cost 2 cents per gram, but an apple and a pear are randomly chosen, what's the probability that an apple costs more than a pear? What's the probability that an apple costs more than a pear? So in part B, we know that apple costs 3 cents per gram, pear costs 2 cents per gram. We're looking for a probability that apple costs more than a pear. That's the probability that 3A is greater than 2B. Since A represents the weight of the pear, the apple, A represents the weight of an apple. The weight times the cost. The weight times the cost per gram. That's the total cost of an apple. And B represents the weight of the pear. The weight times the cost per gram. That's the total cost of the pear. We're looking for the probability that the apple costs more than the pear. That's the total cost of an apple. That's the total cost of a pear. We're looking for the probability that the apple costs more than the pear. Similarly, I can bring A and B to one side, bring all random variables to one side. Bring all random variables to one side. I have 3A, probability that 3A minus 2B is greater than 0. These two probabilities are equivalent, they are exactly the same. Then I create a new random variable. The S is equal to 3A minus 2B. Since A and B, they are independent normal random variables. X is a linear combination of A and B. Then X must also has a normal distribution. Since X is a linear combination of independent normal random variables, then by the previous theorem, X also has a normal distribution. So let's probability that X is greater than 0. Since X has a normal distribution, I can convert X to Z, the standard normal distribution. Then use the table of the standard normal CDF to find the probabilities. That's much easier than solving integrals. So in order to convert X to Z, we must find the mu and sigma of X. Let's find the mu and sigma of X first. Mu of X is the expressive value of X, which is the expressive value of 3a minus 2b. That's the expressive value of 3a plus expressive value of negative 2b. Separate the random variable first, then pull out the coefficient. If I pull out 3, I get 3 times E of A. If I pull out negative 2, I get negative 2 times E of B. Expressive value of A is 180. Expressive value of B is 200. Then 3 times 180 is 540. 2 times 200 is 400. 540 take away 400 is 140. That's mu of X. Next, let's find sigma of X. In order to find sigma of X, let's find variance of X first. Variance of X is variance of 3a minus 2b. That can be rewritten as variance of 3a. It must be addition here. When we separate variance, we must put addition in the middle. Plus variance of negative 2b. Variance of 3a plus variance of negative 2b. We must consider this as 3a plus negative 2b. If we write it as variance of 3a minus variance of 2b, that's wrong. It must be variance of 3a plus variance of negative 2b. Be very careful. Then pull out the coefficient. Separate the variables first, then pull out coefficient. If I pull out 3, I must square 3. I get 3 square times variance of A plus negative 2 square times variance of B. 3 square is 9. Variance of A is 15 square. Negative 2 square is 4. Variance of B is 25 square. Then here I use my calculator. 9 times 15 square plus 4 times 25 square. I use my calculator. I get 4,525. That's the variance of X. Then for standard deviation of X, take square root from the variance of X. If I take square root for variance of X, I get square root of 4525. Leave it the way it is. Then, since I know mu and sigma, I know the mean and the standard deviation, I can convert X to Z, convert X to the standard normal distribution. The formula is 0 minus mu of X over sigma of X, radical 4525. Then here use calculator. 0 minus 140 over radical 4525. If I use my calculator, I get negative 2.08. Use your calculator, round the answer to two decimal places. I get negative 2.08. Then, since we try to use the table of the standard normal CDF, I must write probability in the form of probability Z less or equal to some constant. So here I can use the complement. Write it as 1 minus probability that z is less or equal to negative 2.08. Then this is phi of negative 2.08. Use the table, find phi of negative 2.08. Negative 2.0 is here. A is here. Negative 2.08 is 0.01876. 0.01876. Let's check. I get 0.98124. If I round the answer to 4 decimal places, that's 0.9812. In general, round the answer to 4 decimal places. That's 0.9812. Part C. When 3 apples and 2 pears are randomly chosen, what's the probability that the apples weight more than the pears? Part C. When 3 apples and 2 pears are randomly chosen, what's the probability that the apples weight more than the pears? Part C. Be very, very careful here. Part C. We are looking for probability that 3 apples. What's the probability that 3 apples weight more than 2 pears? 3 apples weight more than 2 pears. 3 apples with more than 2 pears. Probability that 3 apples with more than 2 pears. That's a very, very common mistake. That's a very, very common mistake. Probability that 3 apples with more than 2 pears. Be very, very careful. That's wrong. This is wrong. 3 apple means 3 different apples, not the same apple. Not the same apple. 3 apple means we're choosing 3 different apples, not the same apple times 3. 2 pairs means we're choosing 2 different pairs, not the same pair times 2. That's a very, very common mistake. We're looking for probability that 3 pairs with more than 2 apples. That means 3 different pairs. When we choose 3 pairs, we choose 3 different pairs. 3 different apples and 2 different pairs. That's the weight, total weight of 3 different pairs. That's the weight of 2 different pairs. That's the weight of 3 different apples. That's the weight of 2 pairs. That's the weight of 3 apples. We're looking for the probability that 3 apples with more than 2 pairs. That's the weight of 3 pairs. That's the weight of 3 apples. That's the weight of 2 pairs. We're looking for probability that the weight of 3 apples is more than the weight of 2 pairs. Be very, very careful. If you find probability that 3A is greater than 2B, that means you are using the same apple 3 times. You are using the same pair twice. When we choose 3 pairs, usually we choose 3 different pairs. When we choose 3 apples, we choose 3 different apples. When we choose 2 pairs, usually we choose 2 different pairs. So that's wrong. It must be probability that A1 plus A2 plus A3. The sum of 3 apples, the weight of 3 apples, is more than the weight of 2 pairs. So similarly here, we move all variable over. Move all random variable to one side. If I move all random variable to one side, I have probability that A1 plus A2 plus A3 minus B1 minus B2 is greater than 0. Let me call this random variable x. Let me call this random variable x. The s equal to A1 plus A2 plus A3 minus B1 minus B2. Since a and b, they are independent normal random variables, and x is a linear combination of independent normal random variables, then x, by the previous theorem, x must also has a normal distribution. By the previous theorem, x also has a normal distribution. Then here a1 plus a2 plus a3 minus b1 b2 become x. Since x has a normal distribution, I can convert x to z, the standard normal distribution. In order to convert x to z, we must know the mu and sigma of x. We must know the mean and standard deviation of x. So let's find the mean and standard deviation for x first. Let's find expected value of x first. Let's expected value of a1 plus a2 plus a3 minus b1 minus b2. That can be written as expected value of a1 plus expected value of a2 plus expected value of a3 plus expected value of negative b1 plus expected value of negative b2. Then I can pull out negative 1. For b1, b2 I can pull out negative 1. That's expected value of a1 plus expected value of a2 plus expected value of a3 minus expected value of b1 minus expected value of b2. Expected value of A of the apple is 180. Expected value of pear is 200. So I have 180 plus 180 plus 180 minus 200 minus 200, which is 540 take away 400 is 140. That's mu. That's mu of x. Next, let's compute variance of x. Let's compute variance of x. Variance of x is variance of a1 plus a2 plus a3 minus b1 minus b2. When we're looking for variance of the sum of several random variables, I can separate the variance. Write it as variance of a1 plus variance of a2 plus variance of a3 plus variance of negative b1 plus variance of negative b2. Then pull out coefficients. When I pull out coefficient, I must square the coefficient. I get variance of a1 plus variance of a2 plus variance of a3 plus negative 1 times variance of b1 plus negative 1 times variance of b2. And then we know that for the apples, variance is 15 square. For pears, variance is 25 square. So I get 15 square plus 15 square plus 15 square. For variance, if I pull out negative 1, I must square negative 1. Negative 1 square is 1. Variance of b is 25 square. Negative 1 square is 1. Variance of b is 25 square. Then use calculator. 15 squared plus 15 squared plus 15 squared plus 25 squared plus 25 squared. I get 1925. That's the variance of x. Then for standard deviation of x, for the standard deviation of x, take square root for 1925. We can leave it the way it is. Then here, once I know mu and sigma, once I know the mean and the standard deviation of x, I can convert x to z. I can convert x to the standard normal distribution. Here I use 0 minus mu of x divided by sigma of x. It's vertical 1925. Then use calculator. Round to 2 decimal places. Use calculator. Round to 2 decimal places. Here I get negative 3.19. Use calculator. Round to 2 decimal places. I get negative 3.19. Since we try to use the standard normal CDF, the table of the standard normal CDF, I must put probability in the form of probability that z less or equal to some number. So here I can use complement. I use 1 minus probability that z is less or equal to negative 3.19. That's phi of negative 3.19. Then use table, find phi of 3.19. Phi of negative 3.19. Negative 3.19 is 0.00071. 0.00071. Then subtract, I get 0.99929. Then round the answer to 4 decimal places. I get 0.9993. In general, round the answer to 4 decimal places. I get 0.9993. That's part C. Part D. When 3 apples and 2 pears are randomly chosen, what's the probability that the average weight of the apples is more than the average weight of the pears? What's the probability that the average weight of the apples is more than the average weight of the pears? How do we find the average weight? How do we find the average weight? Average weight of an apple is, we find the total weight of the apples. Find the total weight of 3 apples, then divide by 3. That's the average weight of 3 apples. It's more than the average weight of 2 pears. We find the total weight of the 2 pears. That's B1 plus B2. Then divide by 2. That's the average weight of 2 pears. That's the average weight of 3 apples. That's the average weight of 2 pears. We're looking for probability that the average weight of 3 apples is more than the average weight of 2 pears. This can be rewritten as probability that 1/3 of A1 plus 1/3 of A2 plus 1/3 of A3 is greater than half of B1 plus half of B2. Then we move all variables to one side. Move all variables to the left side. Then move all random variables to the left side. This probability can be rewritten as 1/3 of A1 plus 1/3 of A2 plus 1/3 of A3 minus half of B1 minus half of B2 is greater than 0. Then let's call this random variable x. Let's call this x. Let x equal to 1/3 of A1 plus 1/3 let me put it here. Let s equal to 1/3 of A1 plus 1/3 of A2 plus 1/3 of A3 minus half of B1 minus half of B2. Since X is a linear combination of independent normal random variables, then by the previous theorem, X must have a normal distribution. Now X has a normal distribution. So this property can be rewritten as probability that X is greater than 0. Next, I can convert X. Since X has a normal distribution, I can convert X to the standard normal distribution. In order to convert X to the standard normal distribution, I must know the mu and sigma. In order to convert X to the standard normal distribution, I must know the mu and sigma. I must know the mean and the standard deviation of X. Here, let's find the mean and the standard deviation of X. Mu of X is E of X. Here, X is 1/3 times A1 plus 1/3 times A2 plus 1/3 times A3 minus half times B1 minus half times B2. Then I can separate the terms. I can separate the random variables. A special value of 1/3 times A1 plus a special value of 1/3 times A2 plus a special value of 1/3 times A3 plus a special value of negative half B1 plus a special value of negative half B2. Then I can pull out coefficients. I get 1/3 times E of A1 plus 1/3 times E of A2 plus 1/3 times E of A3 minus half times E of B1 minus half times E of B2. E of A1 is 180. E of B is 200. So I got 1/3 times 180 plus 1/3 times 180 plus 1/3 times 180 minus half times 200 minus half times 200. Here I use my calculator. I get negative 20. That's mu of X. Next, I try to find the variance of X. Then take square root, I can find standard deviation of X. Next, I try to find variance of X. For variance of X, let me put it here. That's for part D. It's part D. Variance of X. That's variance of 1/3 of A1, 1/3 of A2, 1/3 of A3 minus half of B1, half of B2. Then since A1, A2, A3, B1, B2, they are independent random variables, I can separate each random variables. Right, that's variance of 1/3 times A1 plus variance of 1/3 times A2 plus variance of 1/3 times A3 plus variance of negative half times B1 plus variance of negative half times B2 Then pull out coefficient. For variance, if I pull out coefficient, I must square the coefficient. For variance, if I pull out coefficient, I must square the coefficient. I get 1/3 square times variance of A1 plus 1/3 square times variance of A2 plus 1/3 square times variance of A3 plus -half square times variance of B1 plus -half square times variance of B2. 1/3 square is 1/9. Variance of A1, A2, A3. Variance of A is 15 square. Variance of B is 25 square. Let's plug in. I get 15 square here. 15 square here. 1/9 times 15 square. -half square is 1/4 times 25 square. -half square is 1/4 times 25 square. Then use calculator. Here I use calculator, I get 387.5. Use calculator, adding up, I get 385.5. That's variance of x. That's variance of x. Then for the standard deviation of x, take square root for 387.5. That's the standard deviation of x. Now, once I know the mean of x and the standard deviation of x, I can convert x to the standard normal distribution. The formula is 0 minus mu of x over sigma of x, which is radical 387.5. Then use calculator. Round this to 2 decimal places. Use calculator, round this number to 2 decimal places. Here I use my calculator, I get 1.02. That's probability that z is greater than 1.02. In order to use the table of the standard normal CDF, I must run the probability in the form of probability that z less than or equal to some constant. In order to use the table of the standard normal CDF, I must rerun the probability in terms of probability that z is less or equal to some constant. So here I can use the complement. This probability can be rewritten as 1 minus probability that z is less or equal to 1.02. That's phi of 1.02. Then for phi of 1.02, I can find it in the table. For phi of 1.02, find it from the table. 1.02 in the table. Here is 0.84614. 0.84614. Then subtract, I get 0.15386. In general, for the final answer, round to 4 decimal places. In general, for the final answer, round to 4 decimal places. I get 0.1539. That's the probability that the average weight of 3 apples is more than the average weight of 2 pears.